Hello, everybody, and welcome. Can everybody hear me and see me okay? And see the slides online? Perfect. Thanks, Joe. So thank you for being here. This is the second part of the Analyzing Complex Coordination in Social Systems workshop in the Methods for Social Change and Inertia series. We thank the British Academy for funding the series and the University of Greenwich Center for Inequality for their support. Today, Dr. Agnieszka Wieszwalska, Assistant Professor at the Institute for Social Studies, University of Warsaw, will continue yesterday's session to discuss quantitative methods for analyzing complex systems, including functional connectivity analysis. As usual, online attendees can type questions in the Q&A or chat throughout the session. I'll also call on people if they raise hands to ask questions on screen during the Q&A and generally throughout the session. Online, we have automated captioning in multiple languages. If you're more comfortable in a language other than English, just turn on the captions and change the language setting on the top right of the captions bar to your preferred language if available. The session will be recorded and uploaded to YouTube and our archives, and I'll provide links at the end to that archive. So the floor is yours, Dr. Thank you.
Hello, good morning, everyone. Today we will continue with our previous talks and topic. We have been talking yesterday about the concepts that define complex coordination and the underlying structural and procedural mechanisms that can lead a system, especially a social system, to coordinate behavior to complete complex tasks. And we have ended our session yesterday with an example of a qualitative analysis of two social systems and a theoretical framework that provided dimensions to assess their complexity of their structure, the complexity of their procedures, as well as the emergent phenomena that those systems displayed. And today we will move a little bit more towards quantitative, quite some towards quantitative methods of measuring complex coordination. But at the start, I would just like to mention that as a social scientist, I do value both approaches, right? So we will be talking about more, let's say, concrete measures here today. But let's not forget that actually understanding a very complicated, not only a complex, but very complicated social system is the same as any other social process or social construct. To get a deep understanding, qualitative studies are actually very valuable, and they can actually guide what kind of quantitative measures you develop or should develop to actually capture the nature of the system, and in our case, the complexity of the system. So it's usually good to have a mixed method approach where you at least have an initial phase where you deeply analyze theory-guided coding or theory-guided dimensions. You analyze qualitatively a system on some cases, examples of its functioning, and then only move to quantitative methods once you know what exactly do you want to measure. So today we will be thinking about how to measure the complex coordination but in a system, and we'll come back to Wikipedia. But of course, since we are using quantitative measures, we will be simplifying. So that's also kind of a note to make at the beginning. We will be necessarily simplifying our system to be able to measure and think, and we will be measuring specific aspects of its coordination rather than general complexity. So again, I would strongly recommend to use both approaches, both qualitative and quantitative approaches, if you really want to assess the complexity of a system. And just a short recap here. We have been talking about how complex systems increase their complexity, right? So the basic ones are the very simple structures and, for example, with exactly the same elements that behave in exactly the same pattern, that have like only one type of interaction or mechanism of interactions. For example, they, I don't know, sum their signals. Incoming signals will produce something at the end. And yes, even in such a simple system, you can actually get at the level of the system a very complex spatial temporal patterns of coordination, which is very nice. But that's like the one point. If you go to a more complex systems, we usually observe the fact that the elements diversify, they start to behave in a variety of ways, and the influence they exert on others is also described by many different mechanisms, right? It's not only, for example, conformism, but there's other, for example, effects of social influence and so on and so on. These aspects of complex system will always be kind of, we have a dimension, and the system can move on each of those aspects from a simple one to a more and more complex one. And if you think about it, like, how do we actually assess whether something is complex when you observe it, right? Because when you construct it, you can actually, or you create an agent-based model, you can actually like input as many complications into the system as you want, right? And as is sensible to actually put in there, because at some point you stop comprehending the whole things and you are unable to actually draw conclusions or just understand what causes what changes at the system level. But when you observe a system and you don't know its mechanics, and you just see the behavior of the system at the system level, right? Or you sample a few elements and you see the behavior of those elements. Like, how do you know if it's complex or not, right? What makes it complex, really? It's worth noting that a lot of systems that are actually extremely simple can produce behavior that, for example, is not predictable, right? For example, randomness, white noise is extremely complex. You cannot, like, you observe a system that is simply noisy, or that say the majority of its signal is noise, then it's very hard to actually understand what's the underlying rule, unless you know that it's just a random number generator, for example, and has a certain distribution from which it draws its observations, right, or its data points. So, for example, randomness might seem very complex when you observe it, but it's not really complex, right? Similarly, you can see very complex and intricate structures that have a very basic rule underneath them. So, for example, crystals of different types, right? They are very nice in the sense that it can be a complex structure, but again, that might be a very simple rule underneath that describes it in full. We also have chaotic systems, right, that display chaotic dynamics. And this is also a difficult question, right, because the observable behavior may be very, very complex. And actually, it is in practice unpredictable, right? In theory, it is predictable, it's fully deterministic, but in practice, we are unable to accurately predict the future state, especially in a longer time scale. But again, a chaotic system can have just one equation underneath, a quite simple one, right? Linear map. Logistic map, is a very simple system, but that produces very complex behavior. So what is it actually that we want to measure? Like, what is the complexity that we want to measure, and how do we actually assess it? So, of course, there's a multitude of studies and ideas how to measure complexity, but we will always probably move along this dimension of regularity. We will have systems that are completely random, systems that are completely regular, and they both of those extremes are actually quite simple, no matter how complex they look on the surface, right? Complexity is somewhere else, right? It's in between. There is some unpredictability in complexity, usually, that is due to many mechanisms that have a deterministic, probably, impact on the behavior of the system, but they have very small, let's say, variance. They have small fraction of variance that they explain within the behavior of the system. So we will be always trying to find the major kind of rules that govern the system. But keep in mind that there may be many more. So many rules is something that many intricate rules of varied importance are what describes the complex system. And there have been theories to measure complexity from a theoretical standpoint. And I'm just giving you here two examples that are very common, right? Commonly used to describe something that is complex, like complex behavior. So the first one is dimensional complexity. So this is a measure that will try to assess the number of independent components in the system. Thinking again, like, if complexity means a lot of rules, so we have a lot of components that have different rules of behavior, then the more of those components, the higher the complexity. Now, this has a problem that, of course, if we have a set of elements that are completely independent of each other, but they kind of like, for example, in one physical space, and we think they are a system, we might assess they are complex, but in fact, they are just not interacting at all with each other, right? So this is not applicable to all cases. Now, the second measure is extremely popular. This is algorithmic complexity. You might have heard of it. This is basically the idea that you can measure the lines of code that would be used or would be necessary, the minimum number of lines of code that would be necessary to reproduce the behavior of the system. Right now, this is like, you don't even have to fully understand the system. You might actually not understand the underlying principles, but you can try and attempt to model the behavior, right? So basically create a sequence of bits that is equivalent to what the system does, and try to reproduce it with a simple code. And the problem here is, of course, that you have a random system. That's actually even impossible. You can write the code and write the code and write the code, and you will never finish, right? There's just no way to do it unless you know that this is a random system that has a Poisson distribution or whatever, right? Then you can just write one line of code and you can fully capture the system. So it's quite difficult to do this. And of course, once you know the rules of the system, it kind of becomes obsolete. Like, why do you need it really? So there's really not an ideal, there does not exist an ideal measure of complexity, but we will here try to use some measures that stem again from the study of the human brain, which again, we understand as one of the most complex systems that we are studying, that we know of. And those measures are based on information theory. So basically, we treat complex systems, and specifically the brain, which is for brain is very natural, right? We treat it as information processing systems, right? Therefore, we could apply information theory measures to see how much information is actually being processed, or rather, in this case, we will be interested in information integration, right? Because again, you can have a multitude of components, let's say neurons, that are not connected to each other, and they can each have their own inputs, signals that come to them. They can respond to them, but even if they process a lot of information, right, that doesn't mean they're complex if they don't, or that it's a complex system if they don't interact with each other. So not the amount of information coming through the system, going through the system is important, but rather what the system does with the information, how much is on the input and what is on the output side of this processing. And of course, first we'll talk about like how it was applied to the brain, to various, actually mostly visual perception. But let's keep in mind again that social systems are also information processing systems. They actually act in an environment by gathering information from outside of the system, from within of the system. They process this information and act on it, right? That's why we also talked about like the importance of coordination and coherence within the system, because once the system is coordinated, it then actually can act effectively in its environment, right? First, we will try to understand how it happens in the brain and what we can measure in the brain, and then we will try to, maybe not ideally, but translate those measures into social systems. So what we know about the brain and how it processes information is that, and we've been talking about it yesterday, is that there's definitely a concurrent segregation of information in the brain and also integration. So we have both divergent pathways and convergent pathways, right? So we know that, for example, at the very low levels of information processing, the signal is generally very segregated. And on the first steps, it actually gets progressively integrated into a bigger representation. So dots are combined into lines, lines into angles, angles into surfaces, and so on and so on. There's movement added to it. And that's how the early stages of processing in the visual cortex happen. So there is the concept of concurrent integration and segregation is very important here. And I think the theory we will be using here is the integrated information theory of consciousness by Tononi. And actually a lot of collaborators of Tononi also contributed to this theory. It's one of the most right now probably most well-known theories of the brain, basically. And it is contested. It is not like the ground truth. So I should mention that probably. But it doesn't introduce a few interesting concepts. And they have actually underscored the importance of the simultaneous integration and segregation, or rather specialization, right? So different areas of the brain are definitely specialized to process specific type of signals input, whether they come from the outside environment or from the body or from different areas in the brain. They have specialization, but our subjective perception of what the brain does is our stream of consciousness, and our stream of consciousness is extremely coherent, right? We wouldn't be able to act on anything or just do anything if our vision and sensory inputs were not a coherent scene, right? And we have the coherent scene changing in time, both like in response when we are in the environment, but of course we also have imagination, we have dreams. And surprisingly, your dreams, even if they are abstract and kind of improbable, they're also coherent, right? You don't see segregated objects in your dreams. They also form a coherent scene because that is what we need to act in the environment. So just to digress shortly, there are people who believe consciousness and this, subjective perception of the whole world, those things are completely epiphenomenal, meaning that they don't mean anything. This is just a side product of the functioning of the brain, and they don't actually arise for a purpose. They are just there because that's how the brain works, and we cannot do anything about it. But there's also a large group of neuroscientists that believe that actually it has meaning, right? That's what allows us to be agents in our environment. So again, we have to have this coherence, but we know that the processing has to start from segregated and specialized units. So how do we actually try to measure information segregation and information integration in the brain? We will start with a very basic concept because again, I'm not sure how you are versed in information theory. So one very basic concept for this, for all of these measures we'll be using today is Shannon's entropy. Do you know Shannon's entropy? That it's not that, I mean, we will not be introducing equations here, just trying to theoretically explain what it means. Basically, entropy measures uncertainty in the system. It's one of the measures of uncertainty. There's a couple, right? Entropy is one of them. It's very widely used and quite simple to compute. And it's also applicable to a lot of systems and a lot of data, basically. You can measure the uncertainty in it. So imagine like a system with like 3 elements. We have here our dice, and each of the system can change its state. Like let's say that they are somehow connected. We don't know how yet, but we observe the state of each element, and we have thus the same state of the system. There is just a sum of those states of elements. And it can assume like we have 6 faces to the dice, to each of the dice, and in effect they have a limited number of. There's a limited numbers of states that the system can take, right? But when we observe, let's say we observe the dice, and we see that they have this state and this state and this state, and like in the time of our observation, let's say as of 10 minutes, we measure it every minute, right? So we have the 10 states. But we can measure it for longer or with a higher frequency, right? We have a sequence of states, and we can actually see how many times each of those states appeared. And if we have the number of times the state appeared, for example, like there's a limited number for our regular dice, but not all of them had to appear, right? We can have only a short fraction of those actually appearing in the system. But if we have those numbers, right, we can compute probabilities simply. See, okay, this state 1 appeared, was the most common one in 1/3 of our observations. We have this one. And the other thirds are a couple of other states for which we compute probabilities. So basically, entropy is a measure that from this distribution of probabilities gives us just one number, which says if it's 0, there is no uncertainty. It simply means that there was only one state visible in the behavior of the system, right? So 100% of times we observed one state. This is entropy equals 0. So we are sure that, like, we can say with a certain certainty that the system will always display this one state, right? Of course, it depends on how well we measure, how long we measure, how representative is the period of time, and so on. But in general, that's what we know about the system. On the other end, we have the entropy equal 1, which means that there was a set of states and each of them was equally probable. So it is not measuring across all possible states, because very often we don't even know what are the possible states. Right? With dice, we know because we know that there's 6 faces of them and we have 3 of them, so there's a limited number of combinations we can have. But for many systems that we observe in nature, we don't know that, right? But we only know those that have actually occurred in our observations. And we can assess, like, if each of them was equally probable, right? So this was just flat distribution of probabilities. Then entropy will be maximal, because basically, like, we have those set of states, but apart from saying, okay, the system can take one of these, we don't know which one it will be in the next step. Like, we have no knowledge of that. We are fully uncertain in a way. So that's how we arrive in our very important measure entropy that measures the uncertainty in the behavior of the system. And from this measure, we can actually measure how well we can predict, like once we know this measure, the behavior of the system if we know a certain part of it. Right? So we have those 3 dice, and we can try to say, okay, we have our entropy of the whole system. We can measure the entropy of one element as well in the system, right? For example, it could be that in the whole system, the first dice was always on the 4, right? And we can say, okay, we are certain about this one element, but if, in all states of the system, it had always 4, we don't know nothing about the rest of the system, right? Because we cannot say anything. It could be any of the states that system attained, because in all of them, the first number was 4. So basically, mutual information measures that, and it's a simple equation including entropies. It's the entropy of the element, then you add the entropy of the rest of the system and subtract the entropy of the whole system. That's mutual information. It's a measure that is like if a component is completely independent from the rest of the system, the mutual information would be 0. There is a kind of another way to measure, but from the perspective of the whole system, to measure again the kind of independence or interdependence of elements in it. And this is called integration. Actually, this measure would be far more useful, I think, for the brain. It's actually easier to understand also when you apply it to social system. So basically, this is the sum of the entropies of each element in the system minus the entropy of the whole system. So we kind of measure the certainty or an uncertainty of each element, sum it over the elements, and then subtract the entropy of the whole system. And this measures how well the information in the system is integrated. Again, if integration is equals 0, that means that, like, really, I mean, if we have the elements, we don't need a system, right? Because they are independent and we know everything, right? Positive values indicate there are some interdependencies in the system. Okay, and once we have those 2 measures, we can actually think about concurrent, let's say, integration and specialization within the system with, let's say, some kind of independencies built in. And Tononi and Edelman first introduced the concept of a cluster index that they specifically actually apply to the brain. And they said that this is a measure that very well describes how the brain is actually structured and how the information processing is structured. But this is, if you think about it, if you know anything about social complex systems and network analysis, that is a very common structure among social networks, really. It's clustering, basically. That means that there are parts of the system that are very well integrated with each other, so interdependent, heavily interdependent, not fully. It doesn't have to be like they behave as one, right? But they are interdependent, but they share much less information with the rest of the system, right? So we can actually, this is the basic measure of structuration. And if you think about clustering coefficient in social network analysis, that's kind of a similar concept, right? Or community detection in social networks basically gives you the kind of the degree to which a system is composed of clusters that are very interdependent within each other, but not across, right? So this measure is simply given by a fraction that is like integration of the system, and then the cluster is for particular cluster integration within the cluster, and divided by the mutual information of this cluster and the rest of the system. And it's important also to notice that when I say about a cluster or component, when we're talking about this, it doesn't have to be one element, right? Like if we're talking about integration or mutual information, we could have said, okay, one dice is our component, we're measuring it, but we could also be like 3 dice, or 3 of them, or 2 of them, or if we have a larger system, another fraction of the system. Right, and this is the moment. Once we know that we can measure these concepts, right? The information integration, information sharing across the system for different sizes of components. That gives us a clue as to how combine it into, let's say, concurrent integration at the low level, and let's say a more interdependence at the higher level. So basically, what we know about the brain and how it achieves this complexity, that it is segregated at the lower level. So there are specialized units that process information. But at the end of it, we actually do have some coherent scene, but it's not coherent in the sense that it's fully synchronized, for example. We know that that's a very bad thing in the brain. So the Tononi actually proposed 2 equivalent or similar measures of what they call neural complexity. And one is based on the measure of information integration, the other on the measure of mutual information. Again, I prefer the first one. But we should start first with the mutual information measure. So basically, this is the average of mutual information for all possible sizes of components of the system up until half, because that doesn't make much sense to go farther beyond it, because you're actually moving, right? If you have half plus 1, that's actually half minus 1 in price. So basically, if you have a system that is composed of a set of elements, you start with components of one element, compute for each possible component of one element, right, for the whole system. You measure the mutual information, take the average, right? Then you take all possible 2-element components, measure mutual information, average, and go this way until you reach the half of the system, right? And then you take the whole average of it, and this is the neural complexity. And it is given by the area besides this red curve. So the red curve is here. I should maybe use a pointer. So this red curve here is the average for each size of the component, right, of mutual information, until you arrive at the half of the system, right? And actually, this equation should give you the area underneath this curve, right? And this is the complexity, neural complexity of the system. Well, in an equivalent way, we can start to measure the same concept using integration. But this time we also go through different sizes of components. But since we measure integration, we have to start with number 2, right? We have take each possible pair in the system and measure their integration. So basically, how much the sum of the entropies is different from the sum of the pair, right? Of the entropy of the behavior of the pair of the elements. And you go until the end of the system, the full system, and you again draw a curve that describes the average for each subset size, right? And if integration, you normally will be linearly increasing with the size of elements, right? And you have this difference between this curve and the linear growth of integration with the size of the system. So again, the area in between those is the neural complexity. Right, so this measure is quite intuitive to understand like how it works. In principle, you expect integration between across elements within those pairs of elements to be rather small. So if you have two cortical columns that each respond, one responds to, we'll see it in a second, horizontal line, one responds to a vertical line in the same part of your vision, then they usually are kind of independent, right? Because they respond to different stimuli. So the integration between those two elements should be low. But as you go up towards the bigger parts of the system, the integration should be growing, right? So yes, we have special units that are rather independent, but the whole system does the thing that we see in our vision. It should be integrated, right? So that's why we started very low, average integration, and as the system grows, we should arrive at a high integration, right? And the more the difference in the way, the higher the complexity of the system, because it shows concurrent segregation with global integration at the top level. Right, those authors, when they were proposing the initial measure, they also did some modeling studies to show how systems of different types of connection structure in the brain should be behaving and what will be their neural complexity. And what they found is, in general, if they copy the actual physiological structure of connectivity in the brain. So here's an example, the top example, which is simply cortical neural assemblies, because again, one neuron is not exactly a unit of analysis in the brain. We have those neural assemblies, and they are they preferably react to specific stimuli. We have those horizontal and vertical lines, and they're of course also kind of oriented in the actual physical space. So like those columns that are near each other, they actually respond to stimuli in spots that are near in your vision. But they, as you can see, there's some that respond to those horizontal lines, some to the vertical lines. And we have those, we're analyzing actually two assemblies, this one here, the blue one, and orange one here. We're looking at their connection structure, not of all the system, because it will be very messy. And they have replicated the actual structural properties of visual cortex, which means that it's called patchy arborization. So like if you have cells within this one cell assembly, they will have connections to another cell assembly and then kind of branch out and have a lot of connections to a lot of neurons within that cell assembly. So this is called patchy arborization. But they also, the density of connection drops with distance. So this is also a well-known fact about the structure of connections in the brain. So basically within those, like their own cell assembly, and with those cell assemblies that they link to, there's those lots of connections, but across the assemblies, there are, of course, a few ones, and they will here be connected also in a preferential way. That means that those cell assemblies that code similar types of stimuli will be more likely to be connected than those that code different types of stimuli. So the horizontal lines will preferably link to other horizontal lines. And we sampled 2 neurons from those 2 assemblies, the blue ones and the orange ones. And we have what is called the local field potential measured from the whole activity of the whole system here. And you can see how it behaves. And of course, if you just know some kind of sign analysis, you do see that there's also quite strong oscillations at times, which means that at certain points, at least parts of the system are synchronized, right? Because if you see those peaks and drops, the amplitude, especially if the amplitude grows, that means a lot of elements are synchronized because they're active in one point and they are inactive at the next point in time. Then in the next point, they are all active, and therefore this their signal sums up, and we have those high peaks and valleys. At other points, you see that there's little synchronization of the amplitude drops, and that's like a very natural signal that you can recall from the brain. We've seen that yesterday with the case study of visual perception from each electrode. Basically, get this thing. Now, in those cases, the complexity of the system was the highest, right? So we see that those specialized units. This is a simulation model where they just put some signal into this network, the neurons process the information, they send it out to their connections through axons. Those cells can also be activated, and that's how you just record the signals. But if they maintained the same similarity of structure, but reduced the density simply, right? So we kind of got rid of most of the patchy vaporization, but the general structure, let's say, of like who links to whom is maintained. We get this kind of behavior, right? The system is generally not synchronizable, right? The elements act on their own, mostly, like fully, but mostly. And what you get is a very flat signal as a local field potential, because basically the elements cancel each other out, right? So some are active, some are inactive, the sum of it is close to zero. And that is where we get the lowest complexity. There's just too much segregation. And in the final example, they actually use a similar density of connections as in the first one, but they drop this idea that connections, that the probability of a connection is proportional to distance. Therefore, you know, we have just kind of random connections, like it's quite dense, but they are quite random. So we have a lot of, proportional to the first example, we have a lot of long-range connections, right? And what it means in the activity of the system is basically a lot of the neurons that are very far from each other will synchronize, right? And once they are synchronized, they produce this kind of signal, which we see very high amplitudes, meaning very heavy interdependence of the system. And the complexity measure, the neural complexity, will be kind of in the middle point, right? This is, well, in principle, we think that systems that are highly integrated should be more complex than the systems that are fully independent, right? So that's why this synchronization gives us some amount of complexity, but much less than the system that display segregation at the low level and integration at the global level. Yeah, so this is now there's the question of how do we actually move forward from here to apply those measures in the system. Now, it's very important that if we have any kind of time data where we have activities, whether these activities are measured as dichotomic, like events happening with a certain frequency in a system, right? Or whether we have some continuous variable, we can apply those measures, right? Signal data basically. I mean, this is information theory. It can be applied to anything. They apply it to the brain, but basically you can do it with any kind of time series. And it's very useful, therefore, because also for the brain, it is kind of independent of the activation level, right? It is a measure of time course rather than the strength of the signal itself. This is very easy for neural data and kind of time series data. But can we actually apply it to like behavior of a social system? It is more difficult. Of course, if you are able to simplify the behavior of the system into time series of some kind, that's of course the first step. So we can imagine like if you ignore the content of communication between people, right? You just analyze, let's say, a group that is working on a task, and you completely ignore the content of the conversation, the length of the conversation, you could probably at least map starting points of people talking, right? Or discussing. And you could see maybe some interdependence in the sense that subsets of the group, even if you don't know what they are doing, maybe assign different tasks. And there are moments in which they're very close in time, speaking close in time. Of course, you wouldn't want to measure it like to the second, because people rarely talk right, at the same simultaneously, because that's not communication. That's an argument probably. But yeah, if you measure it like within minutes, 10 minutes, right, periods, you could see that, for example, those 5 people all spoke within the same period of time. They were synchronized in a way. So, and you can measure it for the whole system, and you can see those subsets probably, and think about applying those measures to a simple time series of the starts of uttering a sentence or something. But this is not only the way we can do it. And of course, that kind of way is also, any way of applying those quantitative measures to a very complicated system will be simplifying, right? But it's just one way of simplifying what happens in the group to the simple time series. But we can also try to see if the structure of interactions within the system displays those kind of properties. And here, the translation of these measures will be less, let's say, direct, because, yeah, I mean, the structure is not time series, right? It's a structure. But there have been attempts, and quite successful ones, to measure concurrent segregation and integration for networks. By Klein and Hoyle, they have introduced a measure they called effective information and measures of determinism and degeneracy of the network that can help us understand whether a certain structure displays kind of a specialization at the local level with integration at the global level. And specifically, these are very well adjusted to measure weighted and directed networks, but in principle, they can be also applied to the simplified versions of undirected and unweighted. Here's the first measure, and it's kind of a component of the effective information. It's called determinism, and it's also based on entropy. Like this is the one thing they share with those information theory measures. They're all based on certainty in a way, or uncertainty. So it's basically a Shannon entropy. So if you imagine a network that is again weighted and directed, and you can track where each element, each vertex in the network links to, you can compute vectors of links for each vertex. So basically, if you have this red node, we are here talking about outgoing edges first for determinism, outgoing edges. So this one links here with the strength of 2, to this node with the strength of 4, and to this node at the bottom with the strength of 1. So basically, we have a vector 2, 1, 4 for this element. We can normalize this vector, again, to see how distributed are the links of this node to other links in the network, only using those where there are actually links. Where there's zero on the weight, so there's no connection, we don't take those into account. And once you normalize it, of course, we get probabilities, right? If you normalize, you get probabilities. So basically, 2 times out of 7, this person talked to this person. 1 time of 7, this person talked to this person. And 4 times out of 7, they talk to this person, right? We have a probability distribution. We compute entropy, which gives us the measure of how certain we are that if, let's say, a message reaches this red person, it will arrive at a certain other person, right? So basically, it's a kind of a probability of the next step of a random walker. Like, imagine the message is the random walker, and it goes across the network, right? And the weights are the probabilities of where it should go next. So if it lands at the red node, with the highest probability, it will arrive here, with a smaller one here, smallest one here, but the other node still has no chance of arriving in the next step. So our determinism is given by simply computing the entropy for each of those elements, their outgoing links, and averaging it across all vertices. In practice, we also subtracted the whole thing from the bounding value of logarithm of n. But in principle, we get a measure of how, on average, determined are the next steps once a message arrives at one node in the network, right? If, let's say, each element only has one link, outgoing link, that will be the maximum determinism, right? So imagine a ring graph. I didn't add directions here, but imagine that each of those elements links like only to the right side element, right? And with they have one connection, so the weight is actually meaningless, right? Let's assume that all weights are equal across the network for simplicity. So that will be maximal determinism. So whenever you land at some local node, you are fully certain where you will be next. So this is maximum determinism you can get. You can also try to measure kind of certainty at the level of the whole network, or the global, let's say, scale. So instead of now looking at the local connection, we sum all the weights. We call this usually average node strength. Like we have average node degree that describes the average of node degree is the number of links. Node strength is the sum of the weights of its links. So it's like how much information goes through this to a particular node. If you average those node strengths across the average the whole strength across the network and the normalized, let's say, weights, that means divided by the sum of the strengths in the network, then again you get a kind of distribution of probabilities, which means like how likely it is that some information that appears anywhere in the network will arrive at a particular node. This means this is sort of also a centrality of a particular node. So think about like if somebody has a lot of strong incoming links, there's high chances that if you spread a rumor across this network, it will very quickly arrive at that node, right? And if we, for each of those elements, we compute this kind of their centrality measured this way, we get again a probability distribution. We compute the entropy from that, and again subtracting from the bounding value, we get the network's degeneracy. The more degenerate the network, the more likely it is that whatever is put in the network lands at a single node. So this is the most degenerate graph you can imagine, because basically, let's say again, I forgot the hours, but if all nodes link to a single node, it's a star network, then wherever you put the information in the maximum of one step, it arrives at one single node. So this is maximally degenerate graph. And on one hand, you can say that this is a mostly integrated information graph, but that's not like integrated in the network. It's actually specialized to a single node. So that's not what we want in our network. So from this, actually, the authors derived one single measure, which is determinism minus degeneracy. They have a one, because they have one bounding value, then this measure is sensible, and it's high when local connections are specialized. So there's high determinism, right? We have the links that we preferably send information out to. But when we look at the globality of the network, right, we want the degeneracy to be low, meaning the information is not trapped within a single sink, right? There's no central point that it arrives to, and that's it. So this is basically kind of a way of measuring concurrent specialization and integration of information in a network. And if you think about it, it's also, okay, these are examples from the article, Klein and Howell, of different, let's say, of course, artificial graph, but well-defined ones with different values of determinism and degeneracy. The ring graph, the star graph, that's a high determinism, high degeneracy. But we have low determinism, which is a fully connected graph, right? Because we can go wherever. And low degeneracy when we have a ring graph with symmetrical connections. They have also shown that well-known structures of networks can be kind of aligned on this measure of effective information from the ring lattice, random networks, fully connected graphs, stars, and also they have only scale-free Barabasi-Albert network. But actually, if you think about the concepts of effective information, you can imagine that small world networks will have high effective information, kind of by definition, because they have sparse but existing long-range connections and very dense local connections. They will be somewhere there. If you think about this measure, it's actually nice to be able to translate it to well-known social science concepts. And specifically, I feel that the one that is most fitting is the social capital. Think about it this way. We have cohesive units somewhere in the network, right? So people who, let's say, have their preferred information sources or places where they can get resources of specific type. But on the other hand, we do not have a lot of those structural holes that would mean that certain people occupy controlling positions in the network. So when I talk about social capital here, I mean the social capital of the group, actually, of the system, not social capital of specific nodes in the system, because those two not necessarily, like, they're not the same thing, right? So if a person has a high social bridging capital, meaning they interconnect other nodes and there are no other ways for information or resources to flow, that person is kind of crucial for the network, but it's to their own benefit. They can kind of draw their power from being this connecting node, but it doesn't mean that the network actually, the whole group works as a effectively in a way. It can coordinate effectively. Just imagine this person, you know, going on sick leave or something like that. Like this is an organization. This is the person who has access to specific resources in one team and specific resources in the other team. The one person is gone. The system doesn't work. So this kind of a social capital is not necessarily conducive to complex coordination of the whole group, right? It will be more kind of for their own benefit. On the other hand, if we have this kind of cohesive social capital, but that does not spread across the whole network, right? You know, fully connected graph, especially in large social networks, right, are extremely difficult to maintain and costly simply, and they are not necessarily a very good thing. So basically, if we have high effective information, you can think that there's a balance between this cohesiveness, but also the spread of information across the whole network and isn't trapped anywhere in a specific part. Okay, I can maybe start the next, the case study and finish it after a break, right? Just a minute more. And this is a very kind of powerful information. Again, it is simplifying. Let's not forget about it. It's kind of simplifying, but we can apply it to many network structures within social systems to see their potential for information integration, right? For like both concurrent specialization and integration of information. And measure how well those kind of, let's say, complex structures translate into actual complex tasks that that group performs, right? Are they actually able to effectively coordinate on a complex task and succeed? And we've done a case study on Wikipedia. Again, we're coming back to Wikipedia. And we've actually been tackling the question, I think it's kind of overreaching in a lot of my research, of why is it that some systems, especially when we talk about those huge online systems that theoretically have a lot of resources, very low cost of coordination, how come that some of them are successful and some of them are absolutely failing? Like most of them are failing, in fact. If you think the number of projects, of websites, of wikis, or, you know, different initiatives, like the vast majority of them basically fails, and only a few of them actually reach any kind of success that is visible to an average person. And Wikipedia is a very, very nice example of that, one of the few. But also, we have been talking yesterday about how Wikipedia is very, very, very complicated in its structure, right? We have a lot of diversity in user roles and in subgroups, right? We had people who were kind of volunteering to do mundane work, for example, and that was one group. The others were, for example, volunteering into more controlling positions like administrators, but there were some also that were volunteering to, let's say, reviews or reviews of a particular type, right? So we had those task related groupings in the Wikipedia. And since we can divide the system into those groups, and we know that they also, all of them in a way, always strive to the same goal to produce encyclopedic articles. We can see which of those groups is actually effective, right? And see whether their structure, the complexity of their structure relates to their success. And that's what we did. And we looked at what is called wiki projects on English Wikipedia, which are the best kind of, say, division units within the Wikipedia for this kind of study, because they're topically oriented. So basically, a wiki project is a group of editors just sign up to work on a specific topic. So they are not like, the type of task is not important, not such as a review, spelling correction, or anything like that, but rather the topic is the grouping variable. And of course, you can imagine that there are topics that are generally better covered in Wikipedia, and those that are very poorly covered. We talked yesterday about the women in red problem, so like basically biographies about women. There's a huge knowledge gap there. But if you think about it, there are, of course, the editor base of Wikipedia, and it has been shown year after year, is mostly middle-aged white men. So we can imagine also that the coverage of specific areas of knowledge is very poor in place. So here, I mean, the size of a wiki project is both determined by the scope of the whole issue they're tackling, like, so we can have, like, I don't know, English history, right? That's a huge topic, and it can be subdivided into smaller ones. And that will be one way, and that will be the most natural way of thinking, okay, those projects will be different in size. But also, there's the thing, again, that depends on the user editor base, is that the size, the scope of the topic is not only dependent on like the actual objective, let's say, range of topics that could be covered, but also popularity. There's just some stuff that is more popular among middle-aged white men than other stuff. And my question is, do you know which wiki project is the most extensively developed and has the best coverage in Wikipedia? Can you guess?
With sports?
No. Kind of similar, but no. Generally, military history. This is the one that's the kind of like stellar wiki project in Wikipedia. It's military history. So we can see that there will be differences, and you know, how do we measure the success? Well, I'm talking about, like, this is the most successful. This is kind of like the flagship example that if Wikipedians were to tell you of what a wiki project is, they will point you to the website of military history. But it doesn't necessarily mean that, I mean, it is also very highly related to the fact that they produce a lot of quality articles. But it's also worth kind of thinking about what it means to be a quality article. Unfortunately, we have nice measures of quality, and while many wiki projects have their own standards to classify or assess something as good or bad, like there are some moments in which the whole Wikipedia community kind of decides if it was good quality or not. We can have a common measure of success for all those projects. And just a few kind of theoretical notes is that it is worth noting that everything on Wikipedia is volunteer-based, right? Volunteer-based. Basically, you are, if you register on Wikipedia, you are a registered user. That doesn't mean you have to do anything. You have an account there, right? And most of the accounts, like there's millions of people registered on Wikipedia. Most of those accounts are inactive, like, and have never been active in the sense of editing anything. So like you can become a member of the Wikipedia, not only a viewer or reader. You can similarly sign up for a project and never do anything, right? So we don't know that. Like, we have to understand that in those types of systems, the membership fluctuates. Some of those projects actually try to maintain an up-to-date list. Like, so if somebody's inactive, they just delete them. But there's just minimal effort required to sign up for such a thing. So this is also, the boundaries of those projects are not exactly very easily visible. But at least what we know about it is that that all of those projects, even if they like have one member or two, they have a common goal, right? And I'm just going to show you here, maybe that's just one thing I do at before the end, just to show you an example of a wiki project. Yeah, that's the one we love, military history. And as you can see, again, we're at the weird space that most visitors to Wikipedia never come to. We are at the community portal. That's the space where all those social coordination things happen. That's not the actual product, right? And you can see that apart from like those discussion forums that we saw yesterday, we also have the space for each project to self-organize. So the Wikipedia as a whole organizes on those community pages. You have the discussion boards, conflict resolution, arbitrary tribunal, and so on and so on. But apart from that, they have the smaller groups that can also self-organize. They can kind of claim a bit of space there and use it to their advantage, right, to coordination. And what we would see is that there's always a mission statement at the beginning, right? So we can see that the task of the group always on the Wikipedia pages. We are a group of Wikipedia editors that work on topics related to military history, theory, and practice, right? What do we do? Our goal is to build the foremost free content encyclopedia of military history in the English by blah, 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 blah. They always usually have displayed this kind of measurements. So how far are they along their goal? And as you can see, they had goals with numbers, indicators, and they are extremely successful in this process. So military history, apart from like this, we will come back to the quality here after the break, but I just wanted to show you how well this thing is organized. Like this is a part of a voluntary kind of group of people who had Wikipedia, and they actually took upon themselves to be even more organized in terms of like, you know, they have the talk page as the usual, always there's a talk page on Wikipedia pages, that's the engine. They have the division into tasks. They have their own newsletter. The Bagel is the newsletter. They send out newsletter, and they are, you know, 2,200 issues already about what is going on, project news, article news, book reviews, timeline, blah, blah, blah. There's a lot of, somebody has to put all this work to actually inform other people. There's academy. They train their members in how to edit military history articles, right? Asking for help, improving articles, citational reference, using statistics, blah, blah, blah. Again, there's assessment which will come again. They have contests to motivate people to do stuff, right? If you are doing something like on an article, you can nominate yourself or other people who work on the article because you think, oh, this has moved so far up in quality. Let's do that. There's awards that you can assign to people. We will have seen that yesterday on user talk pages. If you want to award somebody with something, you can give them this, paste it on their own profile page, right? And there's also like, maybe awarded by any user, any project member, etc., etc. Like, and there's different even levels of those awards, right? If you consider somebody to be extremely good to something, extremely useful to the project, you have membership list, which can be this project is very specific in that it actually tries to maintain this list up to date, right? You have task forces. This is actually interesting. This subgroup of Wikipedia editors is actually divided into further subgroups because there's so many people and this is so active. Again, the most interesting topic on the whole English Wikipedia. Look, fortification, intelligence, maritime warfare, right? This is the task forces. What is I think there's membership hours. The one thing that we also would like to point you out, we were talking about yesterday about like how part of procedural complexity or procedural self-organization is actually building resources within the system that can be accessed by any member, right? So a lot of wiki projects will be producing those, right? So for example, they have guidelines on how to edit articles. They have templates. You don't have to build the article from scratch. You can use a template and just fill some text into it. Like you have specific parts of elements of the website you can use. And there should also, as far as there should be somewhere also a resource for sources, right? Like what kind of knowledge you can cite, where to look for good content online to actually use to produce your article. So that's why we talk about this is kind of this flagship wiki project on Wikipedia. You can see that they're within a very complex complex structure of self-organization in Wikipedia, this thing is like an example of another level of self-organization, right? Where people could do other stuff as well, right, on Wikipedia, and also participate in those discussions in the community spaces. They also take the time and effort to contribute to this. There's also leadership. There's actually, I think, leadership in terms of like they actually elect the leaders of the projects from time to time, who coordinate our project and so on. You can see coordinators emeritus, lead coordinator, coordinators, people who you can also reach out to when you have problems. And there's also interaction, like this discussion is a very important thing. There's a lot of archives of discussion where they talk about what they're doing and so on, and what's happening with the project. So just a short comparison. Yeah, this is a big project, Rivers. That's just one site that covers all this information. This is actually not the least organized one. This is still an active project. By comparison, it just has one page, basically. It has their quality stats, which we'll come back later to. They have a goal, a short goal, what categories of quality they assign to, a short paragraph with maybe if you are here, do something, like please help us with this, related projects, and participants. But basically the largest part of this list is like participants. They still have 80 members, which is not so bad, right? I think this one is probably even less organized. I was trying to find examples of most of the projects look like this. This is just one website, one page with some information that there is a group of editors that does something in a specific area, and you can help with this and this and that, right? So I think we are in for a short break. We have a background ready, and we will try to analyze it after the break. Okay, so coming back to our Wiki projects, we have seen that they vary greatly in how they self-organize, and of course we could have applied qualitative analysis to see those different dimensions and how they score on them. Whether they have a common identity, which we can, for example, measure whether they, on their user top pages, whether they actually mention that they are members of this Wiki project, and so on and so forth. So there is a sample, and we should probably mention there's over 1,500 of Wiki projects on Wikipedia. Let me see, directory of Wiki projects, we can see that they are here, all of them, divided by categories. You can also get some help when you want to start one or divide one into two. There's the whole Wiki Project Council that kind of guides this whole effort. So there's over 1,500 Wiki projects on Wikipedia. But let me see, if you click on any kind of category of those Wiki projects, you see technology, you can see that there's also the Wiki Project Council tries to maintain, let's say, an up-to-date list of which of them are actually active, right? Because again, this is a voluntary-based work. You can add a project, you can work for a couple months, for example, to work on something, but then people either do something else or just quit Wikipedia altogether. This project does not have to continue, and there is no clear way to actually see if it's just less active or maybe not active at all. But there are people who are trying to maintain some kind of list of the projects. There's also, when we're talking about outside tools, there's also a tool provided by some Wikipedia editors, software engineers, that also has classifications of projects of all of them for you to find. So there's some way to browse this huge area. Lost the categories, and you know, if you know that there's a huge number, like quite a sensible sample, we know that they are varied in how they self-organize, to what degree, and we also know that, you know, they vary in scope and size. Scope meaning how many articles they work on, like we're talking about curating those articles, because again, Wikipedia is public domain, so those articles are not owned by the project. They are public, but they are, let's say, curated by the project. So they have this varied scope, but they also have varied membership. We saw that one project had 80 members, another may have a couple hundred members. I think military history has a couple hundred people who at least declared that they want to be parts of this effort. So we know that we could differentiate those projects and how well they organize. That's one thing. We would also want to know how different they are in their effectiveness, right? So we could see that most projects do, like at the very front or close to the front of their, welcome page, they include some kind of measurement of their effectiveness, of success. Now, this is a very common picture here. The goals that they set to themselves, they decided on themselves. Obviously, some projects might be more ambitious and less ambitious. So whether there's a green bar here or a red one, it's not necessarily an objective measure of how well the project, of how effective the project is. It's rather their own idea. But as I said, there's also, interestingly, a process of quality assessment, quality review on probably most of the Wikipedia. And this is a project, a kind of an interesting social process in general, because it's partially kind of up to the project themselves, and partially it's assessed by the whole community. So Wikipedia articles, let me just open maybe some article at least. Whatever. This is an example of an actual content of Wikipedia. And if you click on the top page, you can see the ranking of this article. But you can also see what projects curate this article. And here we should mention that, like a piece of knowledge is not necessarily only classified as belonging to military history or molecular biology or something else. It can be also like of interest to other projects, right? So the assessment here is basically the content scale, but at certain levels, the projects have their own assessments, right? And each project can have a different one. And besides assessing quality, they also kind of assess how central this topic is to their project. So you can see here that is molecular biology only in this effort. It has not been rated as important or not, and so on. There's also task forces here. So like the molecular biology project, just like the military history has task forces within the project, so they can be more specific. And yeah, content assessment is a huge issue where, we could see for this article that was rated C class. So this is like very, very early stage. And the actual articles, each of them, like when you go to the top page, you will see the assessment, you will see assessment for each project that has actually assessed it, right? So there's more, there could be, let me see, maybe I can show you also an article that is assessed by more than one project. Yeah, this one has actually a good article, so this is one, but you can see an article that is actually assessed by many projects, and for some of them, they are high importance, for some of them, they are mid importance, low importance, right? So for some projects, this topic is just less central to how they operate. But once we have an article, I mean, all articles start as stubs, and Wikipedia, preferably, they do not last long as stub, right? This is the kind of level, which means pretty much it has a title, a lead, and that's about it. Then we have a start level article, which is like, it does have some content, but there's very little. With the C level article, just as you could see here, okay, sorry, this is actually a good, it was this molecular biology was a better example. I don't have a C, I think, quality here. But anyway, if you have, this is actually a B class article, so a level higher, and you can see that it already has a lot of content, right? So actually, like if you look at this, like why is it B? Like, why is it not better? Like, why it's not, like, why is it assessed if it's a lot of content, like really lots of content, and it's still not considered of high quality. So mostly those levels start C, B, and sometimes A. Not all projects, not all articles actually have this this level of quality. Are kind of assessed by the project themselves. They have their own assessment rules. And this is the example for description of what it means to be of specific quality for military history, right? Stuff that goes on development will progress, and it's a star class. B class is complete in content, for example, and structure, adequately referenced, includes reasonable supporting materials, right? So this is a B, is actually like a normal article, right? A class is specific. Some projects don't have it, but the B class articles, those that actually are already at a good level, they can be submitted for assessment for a good article. And these criteria for good articles are not specific to projects. They are kind of an assessment scale for the whole Wikipedia, right? So there is, for the lower levels, each project can set their own kind of description, what it means, and they assess whether it actually means those criteria or not. But for good articles, and specifically also for featured articles, these articles have their own criteria that are described and assessed by the whole community. So this is a whole coordination place for assessing whether articles are good quality or not. And in this place, not only you have criteria, instructions, you can nominate, like you see, or you're an editor of Wikipedia, you can nominate which article you think should be assessed. Once you nominate, there should be there are reviews. Each person, whoever, can visit this page and submit a review of this article, even if this is not something that they have been working on. And you can see that yesterday we saw one user that actually was very active in reviews of new articles and articles for creation. They had this kind of their own preference to work on this kind of areas. For good articles, there are also people who like to do that. So they have this common criteria and they go through the list of nominations, they choose an article, and they provide a short review, right? And in the end, also background drives and so on. You have discussions where you can talk about it. There are, and this is very important, creating encyclopedia articles is not a state, and we're reaching a certain state. Criteria change, knowledge changes, and there's also a process of reassessment. Like if you see that the article that was awarded good article or future article status no longer meets the criteria because it's not being updated with new knowledge, you can say, hello, please reassess this. Like either we delete this mark or not. Why is it important actually that there are those marks? Because actually, now if you're a Wikipedia, somebody interested in Wikipedia, you know that when you visit an article, you should look for those marks of good article or not article. I think this one is a good one. There's not a future one, the former future article. You know that there's a small marking, a very small mark at each featured article. Let me show you this. Here at the top, like if you're just a reader of Wikipedia, you would never notice this. But if you're a Wikipedian, that's something to fight for, a featured article. Why is it important? Featured articles appear on the front page of Wikipedia, right? So good article is the kind of basic good level of an article. And this is the first level where the whole community assesses content. Now, if something is actually very, very good, even better than that, and meets additional criteria, you can, in the similar process, really, as for good article, but with more kind of detailed criteria, you can submit it for review for a future article. And again, with future articles, you have the whole process of nominations, reviews, making decision, assigning this little badge here, and if something is featured, it can with certain chance land on the very top of the page, from today's featured article. Only those that have been awarded this mark can appear here. There's also a list of more featured articles. So this is for Wikipedians. They do not get ownership in anything, but they have internal motivations in reaching or achieving a reputation within the community. We could also see at the user top pages of that particular reason we were seeing yesterday, they list their future articles. Their meaning that they have contributed a lot to, right? Again, this is here this kind of intellectual paternity happening. Of course, they did not probably contribute everything, but they're the ones kind of owning the process of improving the article, and they boast about it to other Wikipedians. And this is like a very important thing for Wikipedians to get as many featured articles as possible, and for the projects to get as many featured articles, and also to list, for example, which of their featured articles have appeared on the front page. There's also, of course, a whole coordination process that decides what will appear here, same as for any other section here on the main page, right? Because this is like the most visited part of the Wikipedia, and everybody wants to be here, like land in this place. So that's why we have this process, and this gives us an opportunity to actually assess the effectiveness of the projects using a common scale for all of them, right? Because we can see who succeeded in that. And actually, the first thing to notice is, and that we really try to correlate the number of good articles and future articles. Let me go back to military history and their assessment. All projects have this kind of, they should have, like, where is the table? Oh, they do not display the table. Yeah, this is the table, or a couple of tables, the special projects. This is the whole thing. Yeah, statistics. They list this, like this is their badges of honor. Featured articles, you can see that over 1,500 featured articles. That's a large part of featured articles on Wikipedia, and that appear too. Over 5,000 good articles, right? But you can see also that the distribution is such that most of articles are start level, right? So these are articles that are just started. We know that they should be there, right? This kind of article, but nobody has the time to work on it, right? Or to take ownership of the article in a way and lead it to this highest level of quality. And this creates a little bit of a problem. The first thing is, like, we have done that good article, a simple correlation. Good articles are the number of good articles per project is heavily correlated, strongly correlated with the number of good articles. So basically, we treated the both of them as sum of the score, as score of quality or effectiveness of this project. And it's also important to understand that we have just gone through the kind of the coordination pages where people actually assess those articles, review, do stuff. It is important that we kind of think that if it is a much more complex task for a group to achieve featured article status for any part of their products than it is to create a start article. So that's how we kind of translate the effectiveness in creating featured articles we understand it as a kind of being effective at a complex task, because it is much easier to just create a start article, right? So for a group to actually be able to create a featured article, we think they have to coordinate heavily, and we think that this is the complex task. Now, again, these are heavily correlated, so we do kind of score the projects with the sum of their featured and good articles. But it's also important, we've already seen that some projects are smaller in scope, and not only because the topic is just narrower, right, or broader for some projects, but also because they are less or more popular. Like, you can see that military history has like 100,000 articles that are start level. Like, the total of them is 200,000 articles that they have created. That's like a huge amount of effort. Not necessarily because, again, this is a broad topic, but you can create a lot of stuff and go into detail on many things. So we cannot just take the number of quality articles as a measure of how effective the group is at complex tasks, right? Because that's just not fair. Again, those projects that tackle a small issue could be actually very good at, coordinating, even among a small group of members, to create a few very good articles or future articles. So this is not a good approach, but also, if you think about it, it is not a very good approach to to take like a percentage score, right? This might be the other, way of dealing with this. Okay, so let's say what a fraction of their articles is of good or featured quality. But this kind of like means that projects that actually first create a lot of kind of placeholders content will be scoring extremely low. Even military history will be extremely low. Like they have 200,000 articles. So yeah, sure that they have 6,000 really good quality articles, but still as a very small percentage. And in an extreme case, you could have a project that curates, I don't know, 2 articles, right? And both are very good, right? And that will be like what, 100%. And we would say, okay, they're much better than this one. Doesn't really make much sense. So we're actually thinking a lot about how to address this problem. And we have chosen to actually compute a quality score that is normalized by the square root of the articles, number of articles that they curate. Because in a way, it gives you the kind of fraction of good quality articles compared to the, let's say, the scale of the project, right? Not of number of articles, but how, because we have logarithm at the base of 10, like if you take the root of that, it kind of creates you like how large is this project in general, but not in kind of objective terms, but in a logarithmic scale, what is the scale of it, right? Whether it's really small, really big, medium, and so on. And actually it proved to be very, very good. And in general, if you have this kind of problems, it is good to think about like a family of quality scores, from one that is like the number of this up to the fraction, but somewhere in the middle we have this kind of normalized quality score that will allow us to kind of meaningfully compare projects that differ vastly in scope and popularity. So this is like we have our measure of success, and now we want to measure this whole coordination complexity that I have just talked about. Like we had an example of military history, but we would now want to think how to kind of put this whole coordination process that is very varied across the projects into one simple measure, or a couple, maybe at maximum. No, we were thinking about what constitutes like a measurement of coordination within the project, and we arrived at the simple, measure of communication. Why is it important? Because basically this is a text-based interaction platform, right? The people here, they do, and the most kind of active projects probably do have quite often meetings face-to-face. There are also kind of Wikipedia or Wikimedia events around the world where people meet and talk, but like the vast majority of their conversation goes on Wikipedia. And we have actually seen a couple of ways that people can communicate. One of them is, of course, on the article talk pages, we have seen that, but article talk pages are also a place where editors that do not belong to a project communicate with each other and with the project members. We don't know on an article talk page whether the discussion is just by kind of a visitor who decided to correct some mistake, or whether this is a coordination activity of the actual, members of the projects. So this would be not a very good place to search for this kind of coordination activities. There's the other one is we could look at the project pages, right? Because they have this space, and each of those spaces has a talk page. Primarily, the main talk page of a project is usually a place where people discuss different things. This is, for example, project cryptography, and you can see a couple of discussions. And you can see also people. Discussions on Wikipedia look like this. They are threaded, so each has a section, topic, and they are also threaded that you can reply to each kind of comment. And you have this indented structures of replies. They are deeper. You have to go click again to see the whole discussion. So we can see that this is a possible place where we could track how people communicate, and this could be a sign how well they coordinate in a project. The problem with that is, again, that this place is very often kind of a contact point for other editors of Wikipedia to come and ask something of this project, right? Projects are interrelated. When they need, I don't know, to access resources of another project, people will come here and ask. So basically, this is also not a place. A lot of those discussions are generally with other members of the Wikipedia, and it would be very hard to kind of disentangle those debates. So we have decided actually to go to the user talk pages, right? Because we know that at least those conversations are actually targeted, and they are usually happening among two people. There's rare occurrences where some third party joins in, but it's not very, you have to be kind of very attentive to go to somebody's talk page and join a discussion that that person is having with somebody else, right? And still, if you think about it, a lot of those discussions, some of that is this one. Some of the discussion is kind of socializing, so it's building a relationship. So some that, okay, thank you for doing that. Thank you for, let me see the Wikipedia. Wait a second. There's both the discussions that go on user talk pages, they are both related to the kind of the whole work of a person, but also to particular articles. Let me swing this participants of a one project. If we go to a person talk page, you can see that there is talk on specific issues. Here is about some kind of article, probably conflicts going on with this person. We can see a couple of people interacting here. Specifically, it's the person, the owner of the talk page. So he's being addressed, he or she is being addressed, and there's some other person kind of commenting on the issue. This place, again, it will also capture this kind of socializing aspect, right? Which we think, if we think about coordination processes, is also important. We also want to capture this kind of debates, and they do not happen in general on either Wiki project talk pages or article talk pages, because that's not the place for that. Like any kind of socialization, it goes either through private messaging, which is not accessible, or those direct messaging here on the either talk pages. So what we did was actually scrape all this using Wikipedia API and parse it into threads and then posts where you could see the author of the comment and the owner, so the name of the page, which will indicate who was the owner of this talk page. We have also, if you are interested, the parser for the talk pages, this is not an easy thing, by the way, because Wikipedia the database is the database. This is actually obtained using the API, and the parsing of that content of that Wikipedia. If you look at what it actually looks like. Okay, this looks like this, right? So from this mess, you want to obtain all the usernames and relations between the owner of the page and the person addressing them. So if you want to do that and you would like to analyze talk pages, and this works for all talk pages in Wikipedia, we are actually particularly in this project analyzing user talk pages, but since they are all the same across the whole platform, you can also use this parser to analyze other discussions in Wikipedia. And it's accessible here. I'll put a link on the slide. And we have constructed networks, directed networks first between users by using those talk pages. To actually arrive at networks of Wiki project coordination, we had to, of course, filter those networks, because the person could be interacting with a lot more users by membership lists. So we also gathered all membership lists from all projects, from the all 1,000 projects, using their member lists Like this is the one, the ones that they maintain. So we, of course, this is not perfect, but at least we have kind of a way of assessing who is actually a project, who is a member of the project. And from that, we have reconstructed networks of communication. And once we have the networks, we also, by the way, there was a weighted network because we could also assess how many messages have been sent on a talk page by 2 users. Now, there's also one difficulty in here that there's different customs in terms of communication in Wikipedia, because again, this way of direct messaging is not necessarily what is typical for other social platforms. And there's a custom, for example, right now, it's more common that if somebody addresses you on your talk page, like you respond in that place. But some time ago, it was actually that you would go to their talk page and respond there. That's why we have been avoiding we had to treat the network as undirected, because we're not necessarily seeing who has initiated the contact, like whether this is actually a reply or an initiation of contact. So to simplify, we have actually treated those networks undirected, but we have kept their weight. So we know how often the 2 editors have communicated. So from there on, we had this is the membership list, for example. We had weighted networks and yes, assessment, weighted networks of communication, private communication, let's say, or direct communication between project members. And we had their quality score computed as this normalized fraction of articles. And we also have included some control variables to see which of them actually impacts the quality. Our hypothesis is that the private communication, it is what is the basic coordination processes. So the more complex is the structure of private communication, the more effective the group should be at completing effectively the complex task of bringing articles to future article and good article quality. So that is our main idea. But of course, we have to take into account we have taken into account the scope of the project. We have also taken account the project size, right? Because we don't know. I mean, there has been some results that show that simply the diversity in editorship base or the sheer number of editors editing an article on Wikipedia does increase its chances of going to a higher level of quality. So just as a control variable, we have included the project size and the members. We have also included the intensity of communication as a control variables, right? Because we were interested actually how structure affects this, right? So the complexity of the structure, but maybe, it is probably mediated or moderated by the fact that some people just communicate more in general, right? And send more messages than others. So we have those control variables and fraction of members in the communication network, because again, project size is how many people have signed up, and the fraction is like compute the giant component in the network.
Yeah, so just a quick question. What do you just briefly describe how you extracted the network variables from the text?
The network variables?
Yes.
Oh, we only have an edge list, like basically owner of the page, which is like the top page of user, blah, blah, blah. Then you have the top page and the messages, they are signed.
So this data, how did you extract it from API data?
We have there's I have included here a link even.
Just in case somebody doesn't know how to do that and is interested.
Like, this is not a simple thing. It is just regex, a lot of regex to get to that, because this is a messy text content. We have, Shimon, who was doing this difficult job, has actually produced a program, a code that you can use, download if you like. There's a link on the slides. There's also a GitHub repo if you want to see more documentation on that. There's linked. So you can, it's not something that you can just sit down and do in 5 minutes, okay? We have been working a lot with trying to parse wiki text into meaningful content. It's not easy. It's harder than HTML, basically, to get stuff out of it. Okay. So those are the control variables, and we have computed the three important properties from Klein and Hoel that measure the complexity of the communication structure. So determinism, degeneracy, and effective information. I also included these are simple measures. This is simple. You can write it in a few seconds. It's just sample our code if somebody actually wants to use specifically computed, just a function to compute the entropy, Shannon's entropy, and then given a graph object, we were using the iGraph package in R. It is also available for Python. So we have the graph object. You just, but you can also use straight away a adjacency matrix of a network. So matrix of connection, basically node versus vertex, and the strength of connection on the intersection of column and row. That's basically the data structure from which you can easily compute all entropies. Like we normalize the rows, normalize the columns, and you get entropy measures of that. And from that, you compute the two components of effective information. And then you can also subtract them from each other to get the final score. And as you can see, when we're there's one model, yeah, maybe this is better. We have first computed it only using determinism and degeneracy, and you can see that they are actually negatively correlated. So like this is an interesting thing, right? Because global kind of thing of information is negatively related to the specialization of connections locally, which is interesting. That's why we have then later decided to actually use only the effective information measure, and it was actually a significant predictor of the quality score of the projects. Fraction in communication network, so how many people actually communicate within the project was not significant, but the other control variables were actually statistically significant. So the intensity of communication matters, right? Like the more people communicate, the more effective they are in producing or completing complex tasks. That should not be very surprising, especially again in a place where there's only text communication. Like if you don't do that, you just don't coordinate at all. And the number of project members does matter as well. So there's some kind of relation. Okay, maybe those people, the more people there are, the more kind of knowledge there is in the project, or varied knowledge, especially, or varied skills, or maybe varied even motivations to work, because somebody has to be correcting those spelling mistakes. That's probably the least real thing you could be doing, but yeah, somebody has to do it. So even if you don't have practical knowledge, topic knowledge, this is important contributions. And this is maybe the kind of the most revealing picture here, and the result that translate this model into something that is tangible, more tangible. You can see this is a heavily interconnected network. So those people are actually communicating a lot and among each other, but they do not score they have actually very low score, quality score. Even though they talk a lot, they interact a lot, they are probably a cohesive unit in the sense that they know each other. They probably even meet each other somewhere outside. This is not effective. That's not enough, or not as important for coordinating into complex tasks. Similarly, this network actually has a middle score, right? It's better effective than this one. Like, so the middle one, newspapers. Sorry, I was trying to get you. This one here, a star structure, is actually more effective than this one, right? So there's a lot of talk going on here, but little effects. This one, you can imagine that if there's a strong ownership of a project and the person takes responsibility for a lot of things, they can simply single-handedly produce some percent of good quality articles, just searching for resources within his or her contacts, right? So in this way, this can be more effective than a lot of chit-chat. But this was the one that was actually one of the top projects, United States history, and they had both very effective, very high effective information and very high quality scores. As you can see, this structure, I mean, it's not necessarily a small word structure, but it does, I mean, probably if we apply the small word index, it would also reveal here a high score, right? Because we can see that there is a kind of a core of the project with a periphery that has maybe a little bit more connection with the core, but the core is quite large. It's not a single person, people, it's quite a number of people who actually contribute to the discussion. And again, maybe a short quiz, like which project was the top one, do you think? Like the highest effective, the Q score and effective information. So it's not military history. No, it's not United States history. It's actually tropical cyclones. Which is very interesting. It's interesting for a variety of reasons. We actually tried to do a qualitative part within the study, and we were interviewing people, members of the project, especially those active ones, and we did interview a few of the tropical cyclones projects. It is a project that is, it's not a large one. It's extremely tightly organized in the sense that they do take part in a lot of whole community activities. They fight fiercely to be included on the main page, not only in the future articles, but in the news. And they have this specific quality that they actually tackle an issue that is of great importance. Like we even actually analyzed and published a paper on the whole project itself and the correlation of views of their pages with natural disasters, because those people, they are covering hurricanes basically and tropical cyclones in all of the world. That means that this is a kind of a place, they have a spot in the news section on the main site very often. Whenever something happens, basically, there is an article instantly correlated on tropical cyclones. And there's also a lot of studies showing that, you know, as events kind of happen around the world, Wikipedia is very often, I mean, by tracing the number of visits to Wikipedia, you can actually see the importance of events and how many people are affected, because that's the place where people go for information. And tropical cyclones is one of those places, I mean, that the project takes care of a lot of that stuff. And therefore, they are, I mean, they also, I think, are very motivated to produce good quality, right? To kind of cover extremely fast the events that are happening and give them like good coverage, like avoid fake news and so on. But there's also some negativity of it. This project has been also criticized for kind of capturing discussions. Like, so for example, if there's voting on what will appear in the news on the main page, and there is a hurricane undergoing, right, somewhere in some place of the world, there will be a bunch of people ganging up from the project tropical cyclones to actually take over the discussion and voting. Wikipedia is a consensus base. We were talking about it yesterday, and the complexity of different governance structures and so on. Since it's consensus-based, unfortunately, it is also prone to situations where, you know, those that shout the loudest are the ones that you will hear. So if you are able to gather enough users that are online and in a particular moment will take part in the discussion, you can actually reach a consensus just among yourselves, and the other people from outside your project are not that visible. So tropical cyclones has been criticized for their tool being too well organized, they say, too well coordinated for their own business rather than for the whole project, Wikipedia project as a whole. So there's a negative side to it as well. But it's an interesting case in general, showing also that, you know, military history, even though it's so popular among the editors of Wikipedia, the importance, kind of the day-to-day importance of another issues might be actually the thing that brings something to like the highest quality or effectiveness. Okay, I didn't include them. You also compare the effect sizes. I forgot to include the image here. The effect size is actually, because effective information can be measured in bits of information. We could show that like it's the effects, relative effect on the quality of those three variables is similar, but the variance rate, so the confidence intervals for effective information, its impact on quality is larger than for the other ones. That means that, yes, in some cases, it is less important than for some other projects. But that's basically it. And just kind of short limitations here. This study, of course, we only took a little bit of the coordination activities of the whole projects, right? You could see that there's a lot of stuff that we could have measured. And also in terms of even the communication channels, there's other ways for people to communicate interestingly. So because Cyclones has its own Discord channel, they use IRC, they use other websites to coordinate activities. So we don't have the full picture here, and we are extremely simplified in our analysis, but it shows you that, you know, you can actually use information theory measures to process, to analyze, to measure, assess how a social system coordinates. And they are nice because, again, they're comparable to other things in other systems. And I think, you know, the next steps for us is, of course, trying to maybe analyze it in other places, like including other online social systems, because, again, if they are text-based, you can measure communication networks in a simple way. But also you're trying to go offline, where we can both use the network measures of effective information, but we could maybe attempt to use the kind of the integrated information theory, actually measure time series of events in social system to assess their complexity. So that's it. Thank you.
We had a question online about Buzz. Could the examination of Wikipedia as a social system provide insights into the connections between information processing, social capital, and collective intelligence within other online communities?
Yeah, absolutely. I think, yeah, that's just an exemplar. And of course, Wikipedia is a nice case, not only because it's successful, but because it also has this divisions, right? So we can compare different things within Wikipedia with the same quality scale, but I can easily see how you could do this for other places, especially those that have kind of more complex and meso-level structures than just one system. Like, you know, groups or channels on different media, social media, where you could do that easily, right? As long as you have also access to data. Now, Wikipedia is, again, a great example because everything is open here. And even though we usually don't just download the dumps of Wikipedia because that's just too hard to process, they have the API, which is free for research purposes, right? But if you have access to other social media platforms, to their discussions, then easily you could also produce networks from that and analyze the same way.
I'm very used to network analysis, and this might be more obvious if you're not familiar. You're introducing effective information. You're talking about determinism, degeneracy seems just like centralization. Can you talk about
degeneracy is like
degeneracy seems like a measure of centralization in a network, where one person is sort of connected to the person in the center.
Well,
about
it is a measure of centralization, but at the network level, because normally when you measure centrality, you measure it at the level of nodes, and you can average it for a whole network, but it's sometimes not very meaningful. What it means to measure an average betweenness of the network, it's like, okay, there exist nodes that have high betweenness, or they are not, or they are equal, but you know, you can have bimodal distribution of betweenness, and that will give you a mean in the middle that doesn't actually tell you anything about the network. The measure of degeneracy is a measure for the whole system. It measures like whether there is a kind of a central sink where information flows to. And in our networks, we're also thinking there is a core in those networks that have high effective information. They usually do have a core. It's just that the core is not capturing all the connections, right? Because it's not like there's also other connections, and they are going both to the periphery and both to other core members. So this is a kind of a different approach, and I think it's more meaningful, especially when you want to say something about the whole thing, rather than the position-specific elements in the network.
Actually, the concept of information sync, where you have a network that has information flowing into one network particular position. And apologies to talk about information flow in those circumstances as being hierarchical, as being more typical of more authoritarian organization. So I could hear sort of the question about
Yeah.
but it's a bit different, like
Yeah.
you were saying, from centralization and political structure. Okay. But it does, I think, indicate higher.
Also, if you think about coming back to the brain, like that's a good example of a system with effective high information and this low degeneracy. Because on the one hand, you know that there's areas that are more central, but like what it means central, is it like that you stay alive? Like there are, subcortical areas that basically maintain your body function, right? But they also, we think about the central, or maybe it is the prefrontal cortex, like with all those kind of higher cognitive functions, and you can find those hubs in the network. They are there if you measure the structure, either the functional connectivity or anatomical structure. But like we know, like from our knowledge of the brain, that there is no homunculus that steers the whole thing. So like this is the kind of thing we don't have that, and yet information is integrated, but we don't have this kind of centralized sink or a couple of regions where everything flows and it flows out from there, right? That's the kind of idea. Yeah, we can have that, but it's I think this kind of the results show here that it's not necessarily always the best thing, especially if you think about those kind of systems where, for example, there's a high fluctuation of membership. Like this is voluntary based fully, right? And people, even on talk pages say, okay, I'm on Wiki vacation, right? I'm not here and I don't know when I will be coming back or if I will be coming back at all. Some people have a period of interest, they contribute a lot, they're very active, they do stuff and then they disappear. And those systems have to be resilient to this kind of fluctuations. So somebody has to take up that role. And if they were the sink of information flow, like this network could collapse. So this is important.
If we're looking at these networks in a directed versus undirected way, would the implications of effective information measure be different?
I don't think so, because it is suited to both types of networks. Actually, those network measures are better suited to directed ones, right? But they are applicable also to undirected networks.
Like in real-world systems where you might have information flowing towards sort of one central node, but not coming back out. That, from like an Austrian perspective, would be a terrible way to manage.
And it will have extremely low,
and it would have extremely low sort of flow of information in terms of around the network. Whereas the same network structure
without connection,
bidirectional would be much more.
The thing is, of course, if you measure effective information, or in this case, especially the degeneracy of that network, right? If you have directed links and they show you that everything flows to this one central node, but never outwards from that node, it will have extremely low, like minimal very low effective information, maximal degeneracy, and you just have the full better information about this network. But still, if you do the analysis without those directions, it will still be very degenerate and still very low effective information. It's just you're losing some precision in that assessment. And if you compare this network to another one that does not have also directional edges, you can still compare and say, okay, this one is better at information integration and this one is worse. So especially in these cases, of course, comparing those measures across different types of networks is kind of meaningless, right? So if you have a directed network and undirected network and you have this measure of effective information, you can apply it to this one and to this one. But the comparison would be kind of flawed there. You're building in some error in there because it could show you that effective information for the undirected one is higher, but it can only be because you didn't measure the direction of connections, and it could be actually the same as for the other one. So that I would be careful with that. But if you're comparing undirected to undirected, it should still show you meaningful changes and differences.
Yeah, so that's what I was thinking, is that if you're going to do comparisons, it should be between directed or undirected.
Definitely.
So this kind of approach to network analysis, what do you think? Like, what is the functional aspect of this? Like, why do we call it a functional?
Oh, I think like quantitative measures not always capture it well, but especially if you like use it only a part of the coordination structure. But in principle, the functional part is like what we compare it to. Like we think that if information flow and in general complex systems are information processing systems, right? And we can measure how complex is their information integration. That's the complexity of the kind of the system, but we can then relate it and see if the complex system is actually able to complete a complex task. That's the thing. I always think that the structure of the system should be fitted to what it is performing. And in kind of evolutionary terms, if you think about swarm animals and so on, they're extremely well adapted to that. They do not waste energy on bureaucracy and this kind of additional procedural things. They kind of perform their function with the minimal complexity that is required for a specific function. Now here we have an extremely complex social function, basically. Like I know that people criticize Wikipedia a lot, and then there's comparisons to like standard encyclopedias all the time since its inception, basically. But it has repeatedly shown that the quality is generally quite good, and in comparison to other paper encyclopedias, the product is not a state, it's a process. So it's constantly being updated, and I have seen it also in this review processes. So that means that like this is one of the like extremely complex tasks for a group of people to perform, and especially failure of the other approach, like the expert-based one, shows that maybe a huge system that has a good coordination practices, complex coordination, can actually achieve this in a better way, more effective way, that even small group of experts who are very knowledgeable on particular topics. It's kind of the proof that the wisdom of the crowds does work, but if it's in specific circumstances, right? We have to have this. I mean, if you just people on Facebook to write an encyclopedia, like the whole of Facebook, there's a lot of people there, right? Who write a lot of things. That wouldn't happen. Right? There was even, I think Wired published an article like asking why there are no fake news on Wikipedia. Like, and people, okay, this is an encyclopedia, they shouldn't be. Like, but anybody can edit it, right? So we can think of it that it is not just the number of people, it is not just that it's online, right? There has to be this other aspect, and we've seen like extreme complex coordination there. That is the reason why they happen to be so effective and sustainable. So this is very important. And this, we talk very often about complex adaptive systems, right? This is an example of such system. And I think, communication is also a basis for adaptation, right? Without communicating with people, you cannot change the system as the context changes, right? So for example, if the context changes, Wikipedia has been adjusting its coordination practice to a lot of events. Like at the beginning, for example, there was a lot of vandalism, like a simple vandalism. People just delete articles, because it became popular. There was the first initial, oh wow, there's a nice resource, and people just were, trolling, having fun or whatever, deleting whole things, and they had to develop both social kind of rules of what we do, you can do or you cannot do. For example, there's the 3 revert rule. So if you're arguing with someone and kind of deleting their changes and they are deleting your changes back and you're going back and forth, after 3 of those, you're both banned, like for a period of time. That's you cannot cross this level. You are then enticed, you have to actually start talking to them, because you cannot only edit, and that will be the end of it. They also introduced bots to kind of revert vandalism. Like if something is deleted, like if you delete an article right now, like and especially on English Wikipedia, there will be a couple of minutes, it will be back because it will be a bot that will be doing it. It's not a human anymore. So they adjusted to that when they saw that there's too many policies and people, like the newcomers, or like the number of newcomers is dropping. They introduced these help desks. They introduced special, task forces that are there to to watch who is editing for the first time, a new user, and they are going to their talk page, sending them a private message. Okay, do you need help? So there's a different adaptation that have been going on in response to that. And a lot of that goes to the communication, right? So that's why I think, again, the degree of complexity of coordination has to match the degree of complexity of the task. And the function is like in the both of those. Like it's not like the coordination is the function. No, coordination is there to perform a function this way.
Thank you. That was very. Another question I had was when you were showing the different diagrams of different networks, sort of their degeneracy, other characteristics. In some of them, you had the graph had little networks within the nodes, as well as the bigger network. This was, I think, with
the brain? You meant this one or the Wikipedia networks?
No, the here in the page.
This one?
Yes, that one.
Oh yeah, that's
Yeah, so for A, for example, you have some of those nodes have inside them clear sort of network inside them.
This is actually an effect because they're modeling both neurons and neural assemblies. So the big circles are the neural assemblies, right? But within each of the neural assemblies, there are neurons, right? And so that's the spike trains here. So like the potentials of each neuron, that's just a sample of two neurons from one of here assembly and one of here assembly, but the connections are shown between cell assemblies. So like this cell assembly sets a link here, and within this link here, it goes like to many neurons, not to one, but to many neurons. And this is called the property of this patchy arborization. So like if one cortical column send an axon, and axons are grouped into this kind of pathways, like they are not going everywhere. Like this is one pipe, all axons from one cortical column will go together, and then at the end, in the other cortical column, they kind of branch out to make many synapses there.
What that's right to ask is, can you look at sort of the characteristics of the networks both within the assemblies and within the components and across the assembly at the same time?
Well,
as factors in sort of the overall.
Yeah, include the kind of meso level also. I think you can actually do that, but you will have to, there's the hypernetwork also approach that would be maybe suitable to that, if you're aware of that, like which generally is a method to analyze hyperconnection, so networks of networks basically, and this is one that is suitable. But in here you can also think about averaging the signals, because what they were analyzing here was single neurons, and from the single neurons they were computing this, right, averaging their spikes. But in principle, when you actually measure the brain, you don't, especially in human subjects, you never measure single neurons. At best, like when you have an epileptic patient that has a surgery, you can actually put electrodes on the surface of the cortex and measure maybe cortical columns, depending on the electrode you're using. So actually, you don't measure even single neurons, but you are rather at the level of the assemblies. But I know that, for example, in cell cultures, you can actually measure both. And if you know that there's this kind of cluster and you can identify it, I suppose you could actually do it, and if it gives you meaningful results, it could be. But the measure itself does not exactly differentiate. It's whatever unit you choose, you can measure on its level. So, for example, if you measure a cell assembly, each of them will have this kind of signal, just a wave. Another cell assembly will have another wave, and you can also, see that, measure the entropy of their amplitudes, right? So, for example, how often, at what point it is at a certain level, and apply it at this level, right? But not maybe at the same time at both of those levels.
In practical terms, is there levels of analysis issue when you're looking at things that are nested within each other? So like in structural analysis, for example, you have to consider the nestedness in the mass of it when you're doing statistics around something that's nested. Is that the case as well in these kinds of networks?
That's a good question. From like an information theoretical perspective, I don't think there should be one. But in terms of like the social interpretation of it, you usually have to choose your unit of analysis kind of meaningfully, right? So, for example, here they are modeling at neural level, but this interpretation should anyway be at some higher point. And I think in social system, depending on what you are measuring, what is your research question, you actually should guide with what level you will be, measuring your observation. Like, what is your unit of observation? Is that a single person, or is that a group? And you can measure group output, an average group output, or some kind of indicator of group output at the group level. You don't have to measure it an average, for example, individual behaviors, although that is the simplest probably way, right? That you actually, also in statistics, you can take averages and then work on those bigger units, or you can have single observations analyzed at that point, especially if you have like mixed models where you have random effects, right? Sometimes you, I don't know, you're measuring performance of students and you know, you have the grouping factor of schools or class or something. Sometimes people just simplify it by taking an average, right? And comparing classes or schools to each other rather than going all the way and having all levels of analysis in one model. But it is also possible. And I think, again, that's more, it's not a mathematical issue. I think it should be possible, both of those approaches, but kind of more a theoretical issue of what you are looking for.
From this approach, if you're sort of lower level connections, whatever you want to call it, themselves are the component of the connection structure, the network is itself a component or a factor in sort of the overall assembly network. So I'm thinking something like, you know, how proteins fold, right? You have these compounds coming together, they have their own structure. That structure then determines how the protein folds, right? So there's some convergence going on there.
Yeah, that's true.
If you're trying to look at something like that from something that's lower level to something that's higher level, where there's a causal or not a causal, but like a confidential or nested sort of impact, how would you do that?
Oh, I think, like, again, this depends. For example, if you can, if the structures, like thinking about those molecules, right, protein structures, like if they have some kind of grouping variables, so like you have some that are similar to each other, then maybe it's better because they perform functions depending on those, you know, folded structure, right? Some are able to do something and some others are able to do other things. And if you have similarities within a group, it might be actually meaningful to go on that level rather than measure it on the kind of single protein level. And again, this depends on this variance, like whether if all proteins are completely different and perform completely different things because of their structure, then, you know, no grouping is possible, right? And you have to do it at the lower level, right? So that would be my approach, like thinking whether there's actually patterns in those that we combine, and that's the patterns can be also measured by entropy, really. Like if certain structures are improbable, then you have a probability distribution of like what kind of and any kind of dimensional reduction approach will help you here.
So the research question really has to send.
Yeah, I think it's yeah. Yeah, I mean, in social systems, like I think, for example, a good question is like the financial systems, and you know, there's network analysis that analyzes the structure of financial interdependencies between company, the parent company, and so on, the child company, and so on, and you can see the financial flows and so on. But there's also network analysis that show the board of directors connections, like people actually are on board directors of money companies, and you can analyze it at this level, and it also gives you insight. I don't think you should be doing it in one analysis, but comparing one to the other can show you that effects in one network, like the higher level network, are also partially explainable by the fact that, you know, people who are on the board of directors of 3 companies will not make them compete with each other. That doesn't make sense, even if they are like in theory should be competitors in the market, right? That's the kind of approach. So I think
that would be a qualitative.
I mean, you can measure both networks and see, like, for example, you know, where are the clusters? So community detection algorithm, and see, okay, those companies are kind of financially related. Those people are personally related, and see whether they match this kind of way. Like,
so you can cluster both at everything at both levels.
Yeah.
That's kind of what I've been sort of looking to find out how to do. really exciting that you can do that.
Yeah, and I think also, the multiplex approach is also showing you this. Hypernetworks and multiplexes will be also useful. And they are being, tools that are being developed also right now, which is quite novel ideas.
Not for now.
All right, thanks so much. Any last questions from our audience online?
Oh, actually, given that we're on back on this slide, I have a question. So, this question. When you were talking through these slides previously, and the way of understanding,
This one, or
I think it's really information if you go back to my
this one.
oh yeah, I was interested in how this treats the fact that you have the graphic like the dice roll things. It's very finished, like rolling 3 dice. Those are obviously independent of each other. But just what do you do when you think about social system where the outcomes of those 3 agents are maybe independent?
Well, actually, the idea here was just showing kind of a semi-random process, but I did not imply that they are independent. Okay, of course, physically it's hard to make dice dependent unless you just, I don't know, put a magnet in one and the other, and you roll one, and then the other is not capable of arriving at a certain state. But in general, that's the idea. The whole idea with mutual information is that, like, for example, when you have the independence is, for example, with this example, like one dice has always one state only, and the rest of the system is kind of independent from it. But like you can have a relation, like absolutely in this, and that's why you kind of have this sum of the component and the element, and you subtract from it the whole system. And if there is an interdependence, that's why the measure will be above 0.
Okay, so if there are no more questions online, I will just send you the information about our next session, which will be online only. We have Dr. Roxanne Velasco-Lolian, Dr. Linus, and Dr. Jean-Martina will be presenting one building on social change algorithm as a tool in social chapters. Really excited to see what it comes with. That'll be on October 20. And you can see additional information on our websites, which I am sending you in the chat now. If you have more questions, please do. Thanks so much to Dr. Agnieszka. We really appreciate her sessions these 2 days, and I hope you found the sessions useful and helpful. I know I will be looking into these methods a lot more now that I know how flexible and useful they can be. Thanks again, and have a good day, everyone.